All right, good morning. So my name is Yue Li, and we're from MemVerge, and today I'm very pleasant to co-present this topic with my colleague, Kevin. Kevin, want to make an introduction?
Hello, my name is Kevin Conway, and today I will share some issues that we met before.
All right, thank you, Kevin. So let's get started. So this is the agenda that I'm going to talk about today. So definitely, first of all, I think probably most of you do not know us. So I want to give you a quick introduction on what we are, and what we do. Then we'll dive into our PMDK experience, because what we do is around the persistent memory, and PMDK is one of the most libraries. Especially, I want to talk about our experience with PMEM object, which is one of the most flexible libraries in PMDK. And especially I want to talk about memory allocation and concurrent memory allocation, because this is basically what you do first when you are trying to use persistent memory, right? You want to allocate memory. Then I will conclude. So about us, we're still a very young startup, founded in 2017 in the Bay Area. So we're headquartered in Milpitas, California, in the Bay Area. And we do have R&D teams spread between the US and China. We have Beijing office, and we have also a larger Shanghai office also. So our current focus is trying to build the next generation data infrastructure software powered by the persistent memory. And the current offering is called MemVerge Distributed Memory Object. It's still an internal name, we need to find a better name for it, but that's what it is. And currently we offer the beta version for the early adopters to try. So if you want to learn more about us, or you want to actually do a POC project with us, please just reach to us, check out our demos outside, or actually fill the forms, the beta for our beta program on our website. All right. So what we're trying to solve, the pain points we're trying to solve in data infrastructures are twofold. The first one is we think the storage I/O is still too slow. Even if you MEM SSDs, it's still actually far away from the CPU. So it's still PCIe fast. And the other side is DRAM is actually very fast. However, the DRAM is actually still small in capacity and also very, very expensive. So we're wondering whether there's a solution, a single solution using a single media that actually can make storage much faster and also make the memory bigger and cheaper. And we found a great candidate, which is a new class of memory called persistent memory, aka storage cluster memory, or NVRAM. So this is a type of memory that provides very low latency and high bandwidth that is close to the speed of DRAM. On the other side, also comparing to the DRAM, that also offers much higher density. And they can carry, for example, up to 512 gigabytes per single DIMM. That gives you a single server that carries 6 terabytes memory. That's humongous. So this is more and more like NAND flash now. So as an example, Intel and Micron recently already jointly developed the 3D cross-point technology shown on the right-hand side. So this is the media. And in terms of product, so they currently offer Intel is currently offering two kinds of products. The first one is ME SSD, or namely Optane SSDs, shown on the left lower corner. It looks like a conventional SSD, but performs much faster, 10 microsecond latency, 2 gigabyte read and write bandwidth. The second one, which is newer, it's a byte addressable media. The product, namely the Optane data center DC persistent memory, which is shown in the second picture there. So in this talk, we will probably only focus on the second one, the DIMM part. Although we actually will also do a lot of work on the SSD as well. So the storage cluster memory finally emerged, and Intel this April actually announced the availability of Optane DC persistent memory in Q2. So analyst report says that the revenue of Optane DC persistent memory probably is going to reach about 3.6 billion by 2023. And also, if you look at the media report, you can find out also other major storage vendors such as Toshiba, now Western Digital, or Hynix. They are planning to join this market by 2022, so which even makes this an even larger market. And at MemVerge, what we think is that the key is a software ecosystem. that will be the key for the technology adoption for this persistent memory. And the key of the keys is at our side is that we want to allow the user to adopt this technology without actually modifying or rewriting the applications. In this way, the user can quickly leverage the benefit of persistent memory, and also without also introducing lots of extra bugs or need to try to do lots of know-how studies. So the picture showing on the lower corner here is basically the chassis. If you take the chassis for this new platform, you can see there's CPU, and next to the CPU are the persistent memory themes. That's actually the reason why it's actually much faster is because actually physically actually it's close to the CPU compared to the SSDs. So at MemVerge, so what we offer is the world's first memory converged infrastructure software. So in a simple way to think of this is, first of all, we provide a very thin layer called memory hypervisor. In this memory hypervisor basically abstract away the vendor specific properties of the memory and try to present to the upper layer a distributed memory pool. So this memory pool consists of a DRAM and persistent memory, and DRAM can be used for performance caching purposes. And on top of the memory hypervisor, we build two components. The first component that we're offering is the SCM native distributed file system, which means that you can actually use as a file system. You can open a file, read and write file, or you can also create directories. Just like a normal file system, POSIX file system. On the right-hand side, which is what we are developing right now, is the SCM native distributed memory system. By memory system, what we really means is that we offer APIs such as malloc, free, realloc, new, delete, these kind of semantics, so that actually the user can actually continue allocating in-memory data structures inside us. And you can continue doing so until the whole cluster's capacity runs out. So we actually support capacity expand from multiple nodes. All right. So as a high-level overview on the use cases. So at the bottom level, so we have this hardware platform, so the bunch of compute nodes that carries DRAM, carries the storage plus memory, and carries SSDs. So I want to mention that we do offer the SSD-based tiering solution as well, so it actually allows you to make this solution even much more cost-effective. And then on top of the hardware platform, we offer this distributed memory object software that provides abstractions. Then we offer this abstraction to multiple different applications. Currently, these applications are the applications that we have been able to integrate with. For example, the TensorFlow in the machine learning, or Spark for the big data analytics, or some database such as MySQL, RockDB, key-value stores, or maybe Redis. So, MemVerge here, so now we come to the main topic actually. So MemVerge actually is an avid user of PMDK. So we use the PMDK for production development, lots of components use PMDK. We also borrow lots of ideas to do our own development, and we also use PMDK heavily for prototyping. So inside this presentation, so I want to share some of our stories with PMDK, especially on the PMEM object, as I said, and I want to focus on the memory allocation, which is one of the most important steps to use PMEM. And we believe if you use PMDK seriously, you probably will encounter the problem that we're going to talk about in this talk. And of course, on memory allocations, we're not the first one presenting this topic. Already there's a webinar presented by Usha in the Intel website. There's an Intel webinar on PMDK allocators. It's also a great source for studying this topic. But before that, actually, I want to do a quick survey because I'm not sure how deep this topic is. So I want to know. So can you tell me, like, how many of you actually have used the PMDK? Can you raise your hand? Oh, quite actually, there are a few. Okay. And how about the PMEM object? Oh, okay, less than 5 maybe. Okay, I think I need to slow down. All right. Okay, I think then the next slide I think is good. Is good for this audience group. So I want to say that developing with PMEM persistent memory actually has been made quite easy. it means that you don't actually have to own persistent memory, the real physical device, before actually writing some program for this. So this is actually, first of all, the PMEM support has already become native for the recent Linux releases. For example, if you take the CentOS or RHEL, which have been widely used by internet company enterprise data centers, starting from 7.5, actually 7.4, with vanilla kernel, you'll already be able to support the persistent memory. And of course, everything will be great. Your experience will surely be great if you actually have a real persistent memory device, such as Intel Optane DC persistent memory. I think that's probably the only one currently you can get from the market, besides those battery-backed things. But however, if you don't have those, you can still try to emulate those in the Linux operating system. So doing the emulation is quite easy. Actually, you just you take some of those operating system distributions, you augment the graph with the MemVerge option. This basically means that reserve part of the DRAM and treat it as a fake emulated DRAM device. Okay. Of course, doing I/O to that, you will have basically memory-like speed. It will be much faster. Maybe not much faster, but faster than the persistent memory. It works quite well. According to our experience, I've been developing on PMEM for years now, and it works quite well on VMs. Even we have developers using laptops, and also works quite well on laptops as well. And surprisingly, what we found is that if you emulate the PMEM, and if you do a reboot, power the reboot without plug out the power, the data actually is really like persistent memory. It still survives across the reboot. So it's actually give you quite a good experience on the emulation side. We think that PMDK is really a great start and great libraries for us to use. So it has multiple strengths. So for example, the most important feature is that basically PMDK give you a PMEM native data access. By that I mean that, for example, it provides you a couple of very low-level libraries such as PMEM persist and PMEM memcopy. On the name, it actually looks very similar to memcopy, right? Just like memcopy. It looks very simple, but actually it's very non-trivial. So what it does is actually inside the implementation, try to automatically detect the platform that you are running on, then apply the instruction, CPU instruction correspondingly that can optimize for the PMEM read and write. This is quite important. So think about doing this for yourself and trying to support different customers with different platforms. That will be very error-prone and also very tedious and very difficult. So according to our experience, it's very difficult to make it right in the first shot. So with PMDK, you don't need to actually worry about any of this, and it'll do it for you automatically. So this is great. The second one is also, now that you have PMEM, now right, so then when you write memory, right, the power gets lost. The transaction atomicity is very important. So this also, I think in Andy's talk and other PMDK talk, they also mentioned the transactions. So transaction is also very difficult to implement if you try to implement it yourself, and it's also challenging to make it very fast. And PMDK actually has a great implementation for transactions as well. So you can actually, you can use it out of the box. Also very importantly, it's very versatile. What I mean by that is, first of all, it gives you different kind of allocation styles. For example, you can actually append only logs. You can actually also allocate blocks. You can allocate objects. You can allocate memory, volatile memory from PMEM as well, right? So also it gives you lots of different data abstractions. For example, you can actually use it as raw memory, using this malloc. You can also use it as, for example, object store, use DPM object, and also blocks, and even key value stores. We recently actually participated in a webinar with Shimon from PMEM KP team that you can check out our webinar. So where he presented basically the PMEM QA/PV, which is also quite useful in our production. So, and also, if you use PMDK, actually supports, so the PMDK works on different kind of the drivers. For example, you can actually works for PMEM block device. It also works for something called device DAX. So this is if you're a serious user want to try RDMA today, I think that this is probably the only options. But in the future, PMFS can also use that as well for RDMA purposes. Okay. All right, so that's a high level for PMDK. So linear object. So with this library, essentially at very high level, this library basically allows objects get allocated and persisted in PMEM. Very simple. It just does that thing, right? Allocate the object, read and write, right, and persist. It's just quite simple to use. So if you as simple as create a PMEM device pool using the PMEM pool tool utility, which I will talk more about it. Then just you can use the pool to basically start read and write, allocate objects. Okay, let me show you an example, a quick example here. For example, so here is just a very simple code. The main functions, I see just only one function here. So what we do is first, okay, open a PMEM pool. This is actually the path to the PMEM pool. You can basically ignore these the details, but we're opening the PMEM pool. Then we use the function called PMEM object alloc to actually allocate objects from this pool, right? So that's the how you do the memory allocation. And in this function, what we did is actually we just keep on allocating the memory from the pool until it fails. Okay, it's very simple. Just keep on allocating until it fails. And what we did further is that we count how many objects that were actually successfully allocated. And given the size of each object, we can further calculate, divided by the total capacity of this pool, which is actually currently made to be 4 gigabytes. It's actually quite small. You can actually run this on your laptop. Then we calculate what is the memory utilization. So this is the one thing, the first thing that we care about if you want to try to allocate. If you have a very low utility, utilization rate, then this means that allocate is not useful. But if you, in reality, what the experiment we did with this even very small pool, we found that actually the utilization rate is actually quite good. For example, if you look at let's say this table, the key is actually here the allocation size, the size of objects. Again, we only allocate the object with the same size. So if you look at, for example, let's say 16K, which is this row, the utilization can be as high as 97.4%, right? So others also look like 64K, 256K. They all look actually quite good. The utilization can get close to 100%. Well, if you look at this table, you can also find that okay, maybe there are things that can be actually improved. For example, 1 megabyte. If you allocate 1 megabyte objects, then the utilization becomes 74%, which is actually, I think, pretty low. Okay, but that's not actually what PMEM object really can offer, and this actually can be greatly improved, as I show you in the next few slides. But at the first side, when you see this, essentially when you see this result, then we immediately start wondering why it gives us different kind of utilization, right? Because it's a very simple code and it behaves very differently. Of course, if you know memory allocation, it's very understandable. But again, we want to know what is the reason behind it. So we looked around and tried to ask around. Intel gave us lots of help, and we used the tool called the PMEM pool. PMEM pool is a utility that again you use to create the pool to actually investigate the reason to see why actually the utilization is low for some of the cases. So this is a tool that I highly recommend you to use if you start using the PMEM object. And for example, this is a simple output. If you give the pool the path to the PMEM pool, it will print out this information if you put this info here. So first of all, let me try to explain. Okay, this probably will be confusing, but let me try to explain. So the first thing it prints out is the chunk size. And actually, the chunk is actually one kind of like a higher level allocation units. And allocate the PMEM is divided by into lots of chunks, and each chunk, I think internally is always 256 kilobytes. So correct me if I'm wrong. And also, if you look at it, this is the output after we allocate the 2 megabyte object, so which is this case. So if you look at the output, you can see that. So first of all, there's something called zone. Okay, I'll explain later. But in this zone, it's a large area. There are multiple objects get allocated. For example, each of this actually correspond, in this case, correspond to area that actually corresponding to 2 megabyte objects. So you can see that it starts with chunk 0, and the next object starts at chunk 9. So which means that there are actually 9 contiguous chunks that has been used for allocating, for holding this single 2 megabyte object, right? So if you take this, right, so the total memory use is for each object is 9 chunks. So if you take 9 multiplied with 256 kilobyte with the chunk size, and you take 2 megabyte, you want to allocate 2 megabyte, divided by this, actually, this is the memory utilization. So this is what actually we have. So actually, this actually really explains well on this memory utilization part, right? And always we have been asking, so because you can see that it's actually not so intuitive in the sense that if you want to have 2 megabyte objects, right, then about 8 contiguous chunks is enough. Why do you want to use 9? Why is there are 9 chunks needed for holding 2 megabyte, resulting in a lower utilization, right? So one of the reasons, of course, is that you can see that there's this flag called header. So the header is actually, when you allocate, they actually append a small header that takes a small amount of capacity in front of the object. That's part of the reason why it's actually cannot use 8 chunks, because 8 chunks is not enough for holding the extra headers. And I will tell you later that there's actually a way to actually turn off the headers as well in the next few slides. Okay, so here's basically what we see first. Then we start trying to do more studies, trying to understand what are these, like these terms, for example. And basically, this is what we found out. So essentially, there's this persistent, so deep memory object try to allocate memories using persistent heap. And here's how the persistent heap gets organized. So essentially, the PMEM pool is divided into multiple zones. Okay, like zone 0, like zone 0 here. You have multiple zones, and each zone actually consists of multiple rungs. Rungs actually kind of, when I try to reserve memory, you reserve a rung. Then inside the rung, there are lots of chunks. So each of this chunk, again, is 256 kilobyte. And then when you allocate, actually you not allocate chunks, you actually allocate small blocks. So the blocks is actually the smallest allocation unit here, inside here. So actually inside the chunks, you're trying to allocate blocks. The blocks, you have to use multiple blocks to fulfill the allocation of each single object. Okay. Now with this kind of knowledge, so let's get back to look at another example here. So actually we found out more later, we tried digging into the PMEM pool, and we found actually there are tons of options that you can use. That can even confuse a lot of people actually. But basically what we found is these options are actually quite useful. So if you turn on this -H-C-B, it will enable heap, chunk, and bitmap information. So if you turn on this and try to do that again, this time let's do it for the 1 megabyte allocation. Then you can see that actually brings out lots more information. Now again, the chunk size is 256 kilobyte. And what we found is that you can see that essentially there are multiple rungs, right? The types of rung. So essentially this zone consists of multiple rungs, right? So each rung essentially has 16 contiguous chunks. Why 16? Because the first rung starts with chunk 0, and the next rung starts with chunk 16. So actually each rung has 16 chunks. Okay, and each rung is actually sub-allocated in blocks via the bitmap. Okay, it's very standard the allocation. So the bitmap actually has to be stored in an actual chunk. So that's why there should totally 32, but actually 31 is useful. The one left is used for bitmap the other information. Now if you look at this, you can basically, if you do some calculation, but we'll skip the calculation, you're going to see that I will tell you that each of these sections actually correspond to one single 1 megabyte object. So which means that each rung here is actually can basically fit 3 1 megabyte allocations, right? However, the total capacity of this rung is 16 times 256 kilobyte, which is about 4 megabyte. So if you take this and do some calculation, it's actually the utilization is about 3/4, which is 75%, right? That actually explains the 74.8% utilization rate. Again, this utilization is due to overhead. There's a compact headers here, right? And also, I think definitely ideally you can actually use this and actually fit maybe 4 megabyte for 1 megabyte objects. Okay. So then with this study, right? So then we have to improve the utilization. First of all, PMEM is still kind of costly, and if you're only able to use 70% of PMEM, then you're actually losing money, which is not good. So we have to improve the utilization in production, and we think that 95% is probably a good target, reasonable allocation utilization. So again, so we go to Intel. Intel, please help us. We go to PMDK team. Please help us. Give us some advice on how to improve the utilization. So, and Piotr came to us and told us, okay, just use the custom allocation class. So what is custom allocation class? It is a utilization. It is a kind of like a data structure. Data structure or metadata information that allows you to basically tell the PMDK allocate following these rules. The rule consists of several aspects. For example, you can say what is the allocating unit size? The unit size is the block size, basically. You tell PMDK specifically what block size to use. Instead of choosing by yourself, PMDK itself. Just do what I told you. Then also tell the PMDK how many allocation units that you want to put per run, right? And also very importantly, you can tell the allocator whether to put a header and what kind of header. So it's very fancy that PMDK actually provides all kinds of headers. Whether you want to put a header and what kind of header you want to put. And also the alignment of the units. You can do page align 4K or 2 megabyte. Okay. Now, and if you look at EPM object from today, by default, it actually came with 53 predefined allocation classes. So the allocator, so currently, what I showed, the experiment I showed you is actually the PMDK. If you don't do allocation class, the PMDK is very smart. It tries to actually look at what you want to do and trying to keep the allocation class by itself. Try to make its own decisions, basically. And of course, and then you lose control, right? So it does what it does. It's trying to, so you can see that for the previous two allocations, it actually applies headers there, and which actually may hurt the utilization. So with custom class, you can tell the PMDK, you can try to first define the allocation class using the function called PM object control set. Right? You can set allocation class you want, which I'll show you shortly. And also, then you can allocate, you can then start your allocation by instructing PMDK to use this through the function called PM object xallot. So you can pass the allocation class ID to this function and tell the PMDK allocate using this allocation class. Okay? All right. So let me show you exactly how actually allocation class actually look like. So let's first try to just print out all the default allocation 54 allocation classes in the PMDK. So here we have a very simple code that dumps all the information of the allocation class. So it's first of all, after studying, we found out that the allocation class follows kind of a naming convention. You have to pass in the name, keep .allot class the ID then description. So that actually retrieve the allocation class for you by passing the name. Then we print out what is the alignment size, what is the unit size for what is block size, basically what is the units for block size, units for one. So I was a little bit confused why they call this block. And also the class, what is the class ID that it is. So okay, then again with this schema object control get, you can basically retrieve the information. And here's what we got from by running this simple functions, and you can see that it prints out lots of allocating class. And for example, let's say for this the second allocating class, the block size is 128 bytes. It contains 2045 usable units, and the ID is 1. In total, if you take a look at the total number of class IDs, 53 plus 0 is 54. So the default allocating class, there are 54 of them. And you can see different allocating class has different parameters. And PMDK by default will choose wisely wisely and try to do the allocation for you if you don't use allocation class. If you actually do not specify allocation class you want to use. Okay. So here's actually an example like how actually you can use allocation class, as I said before, to actually do the allocation. For instance, let me try to explain the code. Sorry, it's a bit manual, but let me try to explain this. We have a main function here as before, right? So the main function as before, we have to open the PMEM tool using PMDK open. Then what we did is, comparing to the first naive example, we create a customer allocation class here. So how do we do this? So what we try to do is, first of all, we'll try to create an allocation class. Let's say we want to make this ID 54, so which is the next one that is available as reserved for the user to use. Then we say, okay, we want to let's try to create an allocation class to optimize the utilization for the 1 megabyte allocation. Okay, let's try this and let's see if we can create an allocation class to optimize for that. So what we did is actually we let the alignment be 4K, which is page align, and also you can see that we say, okay, this allocation class has no header. Do not apply any header to this object. Okay, because we have our own way to extract the metadata, we don't need to. Then we let the unit size to be the input parameter, which has been made to actually 1 megabyte. So 1024 times 124 bytes, which is actually 1 megabyte. Okay. So each unit, basically each block is 1 megabyte, and then the total number of units per run is 256. Okay, so interestingly, we found that actually PMDK, after taking this, is actually changed this 256 to 255. So they decided to take away one from us. But I understand the reason. Okay, so with this allocation class, as mentioned, then you have to use maybe, I'm not sure other options, but you can use this operate functions and passing this class ID, which is 54. Okay, we want to say, okay, use our newly created allocation class and to allocate. And you keep on allocating until it fails. And again, we just calculate the utilization rate here. Okay, now let me show you what we got. Very interesting. So this is on the left-hand side before, okay, nothing new. And on the right-hand side is what we obtain by using this allocation class. Now you can see that with here, there are lots of empty slots here, but with here, actually all the slots are actually filled with X, actually gets utilized. And if you, and the quick summary is basically for this result, you can see that, for example, our allocation class is taking effect. For example, if it says, okay, there's a run, per run, there are actually 1,024 blocks, chunks. And in each of the run, there are 255 units. That's why I said we have 256 and decided to take away one from us. 255, and each block is 1 megabyte. This is what we set, right? What we set in the code. So this actually, if you calculate it, actually our software reports that it actually achieves about 95% allocation utilization, which we are quite happy about. Okay. Okay, of course there are many traps that I will mention a few, but basically this is a very good utility. You will probably have to use when it comes to serious use of it. Okay. A few quick tips here. So basically, if you want to use allocation class, it can actually dramatically improve your pool utilizations. Especially, this also in particular works well for us, is that it works quite well actually when you can allocate objects whose sizes actually are chosen from a fixed known square set. For example, if you know that in your application, you are only allocating objects in one of these sizes, right? Then basically what you can do is you can create allocation class for each of this, and then let the PMDK allocator to use this for allocating a corresponding object or the corresponding size. And it will give you very high memory utilization rate. So this is having validated inside our implementation. That's great. Then also, however, I have to warn you. So to find the best custom parameters, it's not that actually not that simple actually. You have to do lots of experiments. Try to play with the parameter unit size and number of units per run, and try to play with the parameters and do the experiments. I strongly recommend you do the experiment. Otherwise, you'll see still bad utilization results. And then after doing experiments, always try to use PMEM pool, this tool that Intel developed, to try to do the sanity check on the results, trying to look at the bitmap to see if you have actually a good utilization rate. Okay. Again, to warn you, actually the improper use of allocation classes actually results in very, very bad utilization. So for example, for the previous example, allocation class we created, you don't really want to actually allocate very small object. By small, I mean like few kilobytes, a few bytes, using our allocation class. Because even if you allocate a 1 kilobyte object, we're going to give you actually a 1 megabyte blocks, which basically is a big waste. Okay. I think so. I will stop here and switch to my colleague Kevin, and he's going to talk about even more tricky issue. That is a concurrent allocation, and you will see that when you actually try to allocate them in parallel, there are more issues about memory utilization and fragmentation. So he will actually give you a quick feeling about it, and we will talk about our solutions that we actually apply. Some of those that apply in our productions. Kevin.
Today, I'd like to share a case that we met in our product development. Because we can see all the previous code example is very simple and all use the single thread. But in the real product applications, actually multi-threading is the common case. So during our coding with the PMEM object library, and we met sometimes we met allocation freeze. And which is very strange to us because after the previous system we checked the PMEM pool and we found there's still a lot of freeze case actually should be used, but we thought that didn't fail. So we did some investigation and we found we did some tests and we found this type of error only happens when we try to use a lot of thread to do the allocation of three in parallel, and we use a lot of different object sets to allocate in one system, and to improve the PMEM pool's utilization, we have to use a lot of customized so this is the condition that the error is happening. So we did some investigation and we found that there's a concept called arena in this PMDK implementation. And so what is arena? As our understanding, and we think the application doing the allocation from the PMEM pool state. And so when at the same time, if there's a lot of thread trying to do the allocation at the same time, it will we need to allow to catch this critical resources. So PMDK already did it for us. But we know there's the lock will impact the performance, especially for the high concurrency environment. So the arena was introduced to solve the problem. When you open a PMEM pool, the PMDK will create a set of arena in the DRAM. And when the thread was trying to allocate an object for the first time, it will be assigned to an arena, and the arena will reserve some memories according to the allocation class configuration you use. So that's caused a problem. Here's our guess. And because we use a lot of different objects. The object set will use a lot of different allocation class. And in terms of PMDK's implementation, if the thread allocate object and assign an arena, and this arena will be used in the future, and it will never change. And the arena will reserve memory for each allocation class. So if an arena was used by different thread and allocate object for very different allocation class, it will reserve a lot of memory. which will might cause the unbalanced use of the arena, because other arena reserve too much memory, and one arena has no enough memory to do the real application. This is what so just like this, different arena to resolve too much, and the thread will fail the application. But in the same time, the PMEM tool still have this space. So to verify our happiness, and we try to write a test program to reproduce this issue with simple code. In this test code, we have two types of thread pool. For the object allocation pool, we allocate a bunch of objects with different size and use different allocation tasks to parallel. And in the another pool, the thread will only do the free. It will take object array and create all object image and in one transaction. And after running this thread pool for a little while, we successfully reproduce the issue that the allocation will fail, and we check the PMEM pool are still free spaces. And surprisingly, we also sometimes running into another issue as a surprise to us, because in the free thread, we also may sometimes fail. And we check the error number is still also no memory available. So we understand that maybe this is because the transaction of this allocation maybe also requires some allocation to allocate like the log entries in the PMEM. So it fails to allocate this log entry, so it fails to run this transaction. So this is the reproduce code for us to reduce this issue. And the first time we met this issue, we used the PMDK 1.5. And we cannot solve this issue because we don't want to change the code of PMDK. So in our own application, we use some workaround to try to avoid this. First, we are trying to, when the allocation failure happens, and we think there are still free spaces. So we can try this allocate in another thread, because another thread might use another arena, and it might reserve enough space to do the allocation. But this actually pretty tricky to implement, and I think this introduces unnecessary complexity for the code. So another way may be simple, but we can try that doing allocate, pre-allocate and free in each thread we use. So this kind of a warm-up arena to do some pre-reservation to reserve some free space to use. But this is actually cannot solve the problem 100%. So currently we are updated to the PMDK 1.6, and this with this new version it provides a new interface. By using this new interface, we can measure, we can control the arena by ourselves. This helps a lot. By using this new interface, we can query which arena we currently use, and we can create an arena by ourselves. And also we can query all the arena status, how many memories it reserved, and of course we can set a thread for another arena before it works. So with this facility, we can come up with some solutions from a simple First, I think it's very simple to understand that we can use only a single arena. Since we can set a thread arena, so we can set all the threads to use one arena. Of course, it's very easy to implement, but it might hurt the comparison, which arena was really introduced before. So it only can work in some not much too much thread. So another enhancement based on this is we can do like an allocation class-based arena. So because we have a lot of different objects with different allocation class, so for each thread who is trying to allocate based on allocation class, we can use that arena to do that. So it will help the concurrency, but it will also has its own problem. If your workflow was using a lot of threads to allocate the object in the same size, you still will fall back to the single arena performance. And another solution is that we can that skill that PMDK to make the choice arena first right for us. But only when the allocation failure happens, in that time we can query the current arena's status, and we can choose the biggest arena available, and just reset our current failure thread to that arena. And I think it's much easier because we try only in the same thread instead of talking to another thread. So it's very easy to do. So we did some tests to verify this solution. In our previous reproduce program, we implemented all these three solutions, and they all work. No allocation failure happened. So after that, we measured the performance result for each solution to allocate totally in 4 terabyte objects. And here's the result. As expected, the single arena has a worse performance. But and for the allocation class-based arena method, it works better. But actually, the best way is trying to retry about it. I think because as we understand, the allocation failure case is a rare case compared to the real cross-thread log conflict. So, this is what we are trying to do. So, this is what I have to share.
All right, thank you. So in summary, as a quick summary, so we think that PMEM actually poses, if you want to use PMEM, actually there's a lot of challenges to the software development and also to the hardware. For example, like high performance, you want to achieve very high performance allocation and read and write access. For NUMA control, for NUMA access, it's a big challenge. Also, you want to achieve high memory utilization and achieve less fragmentation for the allocation. It's going to be a very important topic actually in the PMEM, persistent memory research community as well. Again, I want to say that SPDK, DPDK, PMDK, that's why we come to this conference, is that they are very extremely useful as components in a distributed system. Also, actually, all these DKs, actually, we actually use all of them in our production. So maybe next time we can come to SPDK talks as well, or even DPDK. But PMDK today, so as a way to actually increase performance and productivity for PMEM applications, it really helps the prototype a lot if you want to really do some quick prototype development. So, but it requires, as we showed you, it requires advanced programming techniques and the developer attention. For example, just the example I show you on memory allocation is just only a very small tip of the icebergs. Actually, we encountered a lot more traps that we ever expected. But it's actually, so far, we can resolve all of those, and it actually goes on quite well. And most importantly, I would like to thank the collaboration with Intel. We have been partnered with Intel. We are one of the ISVs on persistent memories with Intel. And together, we think we'll deliver better scalability and performance at a lower cost via this very disruptive pre-PMEM based data infrastructure. So in this area, I will just not mention this, but you can read about it. And most importantly, so we are in the beta stage, so talk to us if you want to try to understand more on what we do. And we are hiring in all these locations. So talk to us if you want to be an engineer working with us on this new technology. All right, thank you.
So I saw you were actually using DevDex. Is there any difference between DevDex and FSDex?
Say that again?
I saw you were using DevDex there.
Yes, so currently we're using DevDex, exactly. So the question is whether we're using DevDex.
Yeah, is there any performance consideration for DevDex over FSDex?
I would say currently no. Actually, if you take a PMEM-FS and memory map a file from the PMEM-FS, I think the performance will be similar. However, as I mentioned in the slide, if you want to use RDMA, so Andy, correct me if I'm wrong. So if you want to use RDMA to send the data from a PMEM to other node, you have to use DevDex. So Linux kernel community recently, initially PMEM-FS supports the RDMA, but now they somehow removed that. And I think Intel and trying to push them to add them back in. So in the future, maybe you can use other device type. Yeah. But what I know is all other vendors trying to do RDMA, you have to use step DACs today.